let's continue on with thermodynamics. Last semester we talked about the first law of thermodynamics. First law of thermodynamics basically states that energy is neither created nor destroyed. We can think of this in a number of different ways. We can say the change in the energy of the system will equal the negative of the change of the energy of the surroundings. That's one way of thinking about it. Another way of thinking about it is that we can all of the energy within the system is either heat energy or work energy. We can relate that. So another way of thinking about it, delta E of the system is equal to Q plus W, where one is the heat and one is the work. And from a practical side of this, we can use the fact that all of the energy that is released by a system is absorbed by the surroundings, and that is equal to the negative of the energy of the surroundings plus, say, the heat absorbed by the calorimeter plus the heat lost, etc., etc. And so we can then use things like calorimetry to measure the heat. And the heat energy is directly related to this idea of the enthalpy, H. Though we often use it as the change in the enthalpy, delta H. And we also related that to the delta H under standard conditions for the formation of a compound, as well as the enthalpy change of the reaction under standard conditions. So all of these quantities came in last semester. So this is all of which grew out of the first law of thermodynamics. Now the second law of thermodynamics, first law of thermodynamics deals with energy. Second law of thermodynamics, where we're going with this process is looking at when reactions are spontaneous. This deals with spontaneity. At the simplest level, a spontaneous reaction is one that takes place. Given a set of conditions, A goes to B. And this is where we've been working. And there's a corollary to this. If a reaction is spontaneous, what that means is the reverse reaction is not spontaneous. And this is, as a chemist, if you want to know whether you should even bother trying to make something using a certain set of reagents, you could use this simple process of thermodynamics to figure out whether or not the reaction would go. So this is what we really say is a measure of spontaneity. So it takes place as written. A going to B. Good example of this is water. Water does not spontaneously boil at room temperatures. Water going to water vapor does not spontaneously takes place. H2O liquid does not boil automatically to form H2O gas. You look at that cup of water on the stove, it's not doing anything unless you crank up the heat. So there is some sort of temperature dependence. Right? So some reactions are spontaneous under one set of conditions and non-spontaneous under others. Freezing of water is a perfect example of this. So, how can we tell when a reaction is spontaneous? Well, we already looked at a number of conditions. A number of conditions in the previous example, and we talked about a bunch of different chemical reactions. And when we think about a chemical reaction, usually some of the things that we see are usually those reactions that have a negative enthalpy, those that release heat, have a tendency to be spontaneous. I'm not saying that all reactions that release heat are spontaneous, but many of the ones we see when we think of a chemical reaction taking place, we usually have a tendency to think of them as releasing heat. But there's another set of reactions that don't necessarily release heat that are also spontaneous. For instance, if you take a little bit of sugar and you pluck it down into water, the sugar will dissolve such that all of the solid dissolves into the liquid. The question is why? Why would that be favored? Why would that be a process? All right. And this is where the second law of thermodynamics comes in. The second law of thermodynamics relates to disorder. It turns out that the universe loves disorder. And the way we talk about this relative amount of disorder is entropy. Notice, of course, in the proud tradition of chemistry introducing words that sound very similar to describe very different things, entropy and enthalpy are two very different concepts. Don't confuse the two. Entropy, as your book describes it, is a measure of how spread out or dispersed the energy of a system is among the different possible ways that the system can contain energy. Disorder. Think of it as disorder. The amount of randomness introduced in the system. The symbol for entropy is S. It turns out that the entropy change of the entropy of the system is equal to K times the natural log of W, where W is what we call the microstates. Number of different combinations that explain potential arrangements. The greater the number of potential combinations, the greater the entropy. We never use this. K turns out to be the Boltzmann constant. The Boltzmann constant. We never use this. Okay, I'm not gonna ask you to calculate the entropy from starting conditions. You can, which is actually kind of nice. All right? More often than not, we can use qualitative examples of examining the qualitative descriptions. Like, we use qualitative descriptions. So we can take a look at water as a liquid going to water as a gas. Which of these has more entropy? Which of these is more randomized? Well, we have water, a liquid, relatively dense, water molecules in close contact, whereas in gas, we have water molecules spread out. So again. So within a same unit of volume, there are many more positions for the water molecules in the gas. We would say that this has a high entropy, this has a low entropy. And since we usually don't really care about entropy so much as the change in the entropy, which is, again, is the entropy of the final condition, minus the entropy of the initial, what we see is that unlike delta H, here in these sort of systems, this would have a high entropy condition. Final minus initial, high going to low, and this would be positive entropy values. So this would have a positive value for the entropy. The more disorder, the more positive the entropy value is. The enthalpy, standard enthalpy of an element is usually typically equal to 0. For entropies, standard entropy change for elements is often non-zero. So in these cases, we have to be cautious. Up to this point, we've been able to, elements in their native state, we have been say 0, 0, 0 using in our thermodynamics work. In thermodynamics, many of the same tricks that we used for simple enthalpy calculations, like Hess's law, where we could build reactions and combine them, we can look at the delta H formations of the react products and subtract them from the reactants and get out an enthalpy change for a reaction. So too can we do this with enthalpies. So too can we do this with the next concept we're going to introduce called the Gibbs free energy. So many of the same tips and tricks that we used in enthalpy work for entropy and for other free energy changes. So this gets us to the second law of thermodynamics. The second law of thermodynamics basically states the following, that change in energy, the change in entropy of the universe should always be increasing. Anything that increases the entropy of the universe is a good thing. Second law of thermodynamics says that in these cases, the change in energy in the universe should be positive. Anything that does that is favored. Now, because within the local universe, our immediate surroundings, you can actually violate this very easily. Second law of thermodynamics says that overall, and so we can actually make things more ordered by expending energy. The net effect of this is actually funny, because the change in entropy in the universe, well, that's equal to the change in entropy of the system plus the change in entropy of the surroundings. So when I go into my kid's room and I start cleaning up the blocks, putting all the blocks back in the box, I am making the system more ordered. But there's a cost of that. My work that I'm doing heats up the environment, and so I'm trading off my surroundings. So what this does is creates more entropy in the surroundings and therefore increasing the universe. So it's always, nothing is free, even in terms of disorder. To make something neat, you have to make something else disordered, which is why my car is clean and my wife's isn't. So I have to edit that part out or else I'll get killed. Edit here. Entropy change usually has the units, or the typical units are usually joules per mole Kelvin. Now this right here should give you a clue that entropy changes are sort of related to temperature. And so the second law of thermodynamics basically says that the entropy is always increasing, and then there's a core third law of thermodynamics, which basically says that the only time you can have an entropy equal to 0, an entropy, that's for a perfect system at 0 Kelvin, at absolute 0. So basically, it's a cheat, and you can't really get there. Now, I like to sum up the three laws as follows. The first law of thermodynamics is you can't win. The second law of thermodynamics says you are going to lose. And the third law of thermodynamics basically says the game is rigged. First law of thermodynamics, energy can't be created nor destroyed. We have to trade energy from one to do work, or we have to trade heat to do work, and the heat and work can be interchanged. The second law of thermodynamics says whatever we're doing, we're increasing the entropy of the universe. Even if we can do something that makes order, there's a cost of disorder somewhere else. Usually that disorder ends up in the surroundings. You can think of it as heat lost to the universe. And lastly, it's sort of the hardest one to sort of conceptualize. The game is rigged. It's like absolute zero is very simple. Related to the heat capacity of a material, how readily its temperature changes with respect